Okay, the fourth correlation technique is codebook correlation model. This algorithm have been developed by correlates events that are generated in network based on the modeling of the network and the behavior of the network components. Because they are based on algorithm, claims are made that they do not require expert knowledge to associate with the event with the problem. The figure shows a generic architecture of an event correlation system where it consists of five components: configuration model, event model, correlator, monitors, and network where the problem occurs. The figure shows that the architecture of the model-based event correlation system, as heading state, that we will refer to the as a codebook correlation. Here the monitors capture the alarm event and input them to the correlators. The configuration model containing the configuration of the network. The event model represents the various events and their causal relationship. The correlator correlates the alarm events with the event model and determine the common problem that caused the alarm event. The next correlation technique is that is fifth one is state transition graph model. As per the examination point of view, this is a very important model. A state transition graph model is used by a Seagate nerve center system. It could be used as a standalone system with a NMS. Figure shows state transition diagram for a ping or response where it contains the ping node and the receive response, where ping node is going to request as a ping and receive a response. A simple state diagram with two states for a ping or response process is shown in figure. The two states are ping mode and receive response. When the NMS sends a ping, it transitions from a ping node state to the receive response state. When it receives a response, it transitions back to the ping node state. This method is how the health of the component is monitored by NMS. Looking to the detailed explanation by considering one more example, it gives a detailed, clear idea of this state transition graph model. The NMS ping a hub when the hub is working and the connectivity to the NMS is good. A response is received for each ping sent, say every minutes by NMS. This is represented by top two states, ping hub and receive response. On left side in figure shown, let us consider the situation when a response for a ping is not received before the next ping is ready to be sent. The NMS typically expect a response in 300 milliseconds. An action is taken by the NMS and the state transition from receive response to ping twice. It is possible that a response is received for a second ring, and in the situation the state transition back to the normal ping hub state. Looking into the figure, it consists of ping hub, receive response, ping twice, that is called ground state, ping three times, ping router, receive response from the router, and finally the action, that is send alarm, will be received. However, if there is a no response for the second ping NMS, the pings a third time, a state transition is now pinged three times. The response for this ping will be causes a transition to the ping hub state. However, let us consider the situation of no response for the third ping. Let us associate that NMS is configured to ping 3 times before it declares that there is a communication failure between it and hub. Without any correlation, an alarm will be triggered and the icon represent the hub would be turned red. However, the hub may actually be working and the working station on it may be communicating with each other. The topology database, the correlator in the NMS, is aware that the path to the hub is via the router. Hence, the failure of the third ping, an action is taken and the system transition to the ring router state. The router is pinged and the system transition to the receive response from the router state. So there are two possible outcome now. The connectivity to the router is lost and no response is received from the router. The system takes no action, which is indicated by the closed loop in the ping router state. Looking into the figure detail. The second possibility is that a response from the router. This means that this means that the connection to the hub is lost, and now the correlator in the NMS triggered on alarm that turns the hub icon red. We notice that in the scenario of the router connectivity failure, only the router icon turn red and none of the hubs connected to it turn red, thus identifying the root cause of the problem. Let us understand the one more model of correlation technique. That is, sixth one is finite state machine model. It is a model-based fault detection scheme uses a communicating finite state machine. The main claim of this process is that it is a passive testing system. It is assumed that an observer agent is present in each node and reports abnormality to a central point. Here we can visualize the node observer as a web agent and central point as a web server. An application on server correlates the events. A failure in a node or link is indicated by the state machine associated with the component entering an illegal state. Looking to the figure of communicating a finite state machine, where it consists of the send request in the client and the server side. In the client side, send request will be there, again the receive response will be there. Again, these two are communicating a response or request. Whereas the server side, again same thing, receive request and the send response will be there, and the sending and receiving will be there in the both sides. A simple communicating finite state machine for a client server is shown. It present communication between a client server via the communication channel. For simplicity, both the client and the server are assumed to have two states each. The client, which is in send request state, send a request message to the server and transition to receive the response state. The server is currently in the receive request state. The server receives the request and transition to the send response state. After receiving the request, it sends the response and transition back to the receive request state. The client then receives the response from the server and transition to send a request state. If either the client or the server enter an illegal state during the transition, the system has encountered a fault. Let us see example. After sending the response of a server, it does not transition to receive a request state, it is a failed state. A message is sent to the central location under the failure condition, either by component itself or by the one communicating with a failed component. Hence, we can observe a similarity between the finite state machine model and the state transition graph model with regards to state transition. However, the main difference is that the former is a passive system and latter is an active one. Hope this concept is very important as per the examination point of view.